Hello, my research topic is zircon growth, dating, and interpretation. I will talk about zircon and how it helps us understand geological time on a very broad scale. Zircon is one of the most important minerals in geology because it gives us not only ages of rocks, but also insight onto the entire history of magma systems and geological processes that it is involved in. Specifically in igneous and metamorphic petrology, it's important because it links mineral scale observations to large-scale crustal processes such as magma evolution, crustal melting, and metamorphic recrystallization. Another key reason zircon is so valuable in geology is because it bridges the gap between microscopic mineral processes that we look at in labs and in lectures to large-scale processes such as tectonic evolution and crystallization and things like that. So this allows us to reconstruct Earth's history over billions of years. So first I'll start with a brief introduction to zircon and radiometric dating, and then go into growth dating and interpretation. Zircon is a mineral with a chemical formula of ZrSiO4, meaning it's a silicate mineral made with zirconium. So zircon forms mainly in igneous rocks, specifically felsic rocks like granite, and it can also be found in metamorphic rocks and sediments. And in sedimentary rocks, which I won't go into because it's igneous metamorphic petrology, these are called detrital zircons. And the reason zircon can be interpreted in sedimentary rocks is because it is so resistant to weathering and can survive erosion and be transported all the way into sediments. Zircon is most abundant in silica-rich magmas because zircon saturation is reached only after significant fractional crystallization. And in felsic systems, zircon will also record a longer portion of the magma's evolution, whereas in mafic systems, it crystallizes later and will only record later stage processes. Okay, back to dating. In terms of dating, there are two types of dating, absolute dating and relative dating. So absolute dating will give us a numerical age in years using radiometric dating, whereas relative dating will give us only an age relative to another, so it'll just tell us the order of sequences. The concept of half-life is especially critical because it allows us to look at radioactive decay as a predictable clock, which makes it much more powerful compared to relative dating, and we can only use it because it decays at a constant rate. So absolute dating uses radiometric methods, which rely on radioactive decay. So this involves a parent isotope, which is radioactive, and a daughter isotope, which forms after the decay of the parent isotope. So measuring the ratio between these two allows us to calculate how much time has passed using their half-lives. We looked at this in geophysics class, but the half-life of uranium is 4.5 billion years. So this allows us to look at rocks as old as the Earth. So zircon, that's another reason why zircon's so helpful, because it has a really wide range of rocks that we can use to date it. So why does zircon matter? Zircon is extremely important for dating because of its physical and chemical properties. So zircon is very durable, has a high melting temperature of over 800 degrees Celsius, and it is chemically stable and non-reactive. Most importantly, zircon incorporates uranium when it forms, but excludes lead, which makes uranium-lead dating possible. So any lead found in zircon today must come from radioactive decay, making it ideal for dating. Another key feature that zircon has is an extremely high closure temperature. So this means that once isotopes are locked in, they are not easily reset unless extreme conditions occur. So this is how zircon can survive metamorphic events and still preserve older cores that gives us information on when it crystallized. So if something undergoes metamorphism way later on, we can still look back at its original crystallization age. Now moving on to zircon and how it actually forms and grows. Zircon forms during magmatic crystallization as magma cools. So it grows and it incorporates trace elements such as uranium, thorium, and rare earth elements, which is abbreviated to REE. These elements help us interpret the conditions of the magma at the time zircon formed, and this is done based on the chemistry and concentration of different elements within the zircon. And zircon typically crystallizes from the melt once the zircon saturation is reached, so this is late in mafic systems and early in felsic systems, and this can affect how much of the history gets recorded, which is why we mainly look at felsic systems with uranium and lead dating. One of the most important petrological features of zircon is oscillatory zoning. So oscillatory zoning refers to the concentric growth bands that form as a crystal grows. So an analogy I like to think of is rings on a tree. Gives you different information, how it can tell us how old something is. Or another example we just recently looked at in sedimentology, ooids. So ooids are carbonate grains that are covered in concentric layers, and the concentric layers tell us about the chemistry at that time. So you can look at each different layer and it will tell you something different. So each zone, it's called zoning, so each zone has a different concentration of the trace elements I mentioned, uranium, thorium, and rare earth elements, and these zones formed due to fluctuations in temperature, pressure, and melt composition during the crystal growth in a magma system. Here's a bigger picture. You can see each band here. And zoning tells us lots about the zircon. So it tells us about the evolution of the magma system, changes in the composition, the crystallization conditions over time, things like that. So essentially each growth band is just a snapshot of the magma at that time. So for example, increases in incompatible elements such as rare earth elements can indicate progressive fractional crystallization, indicating that the melt has become more evolved over time, showing the magma evolution. Crystal shape will also tell us about the environment in which it formed. So in felsic magmas, zircons will grow earlier and they're larger and more elongated and they form an open space, whereas mafic magmas, zircons will form later and they're smaller, more rounded, and they grow in tight spaces between other minerals. This is important because it links crystal morphology to the magma composition, and in felsic magmas, lower nucleation rates and higher melt fractions allow crystals to grow freely, whereas mafic systems, the high crystal content really restricts growth, as you can see in the picture on the right. So the complex growth histories of zircons makes it challenging sometimes to date things, but zircons will form deep in the crust, in magma chambers, or in shallow crust environments, but they also move around within the melt, and as they do this, they will record different conditions over time. So zircons in a rock will record multiple different ages, and they get transported through magma reservoirs that are constantly changing, and this means each individual grain records conditions from multiple depths and temperatures. This process also contributes to the formation of inherited zircons, which I'll mention again later, but this explains why zircons from a single rock show age distributions up to 1,000 years instead of just one absolute age. Now, in terms of actually dating zircons, when we date a zircon, we can get multiple ages from a single crystal, and this is because different growth zones form at different times. So instead of one age, we'll get the age distribution that I just mentioned, and these can also be interpreted as magma recharges when new magma enters the system and triggers new zircon growth. There are also several complications within zircon dating. So loss of lead can make ages appear younger. So the daughter isotope that gets measured from uranium lead dating will be too low if there is a loss of lead. And lead loss is particularly important because it occurs along cracks and radiation damaged zones and grain boundaries within the zircon, which leads to discordant ages. Inherited zircon gives older ages because inherited zircons come from pre-existing rocks. These get incorporated into younger rocks without being fully melted. So in other words, the clock doesn't get reset. It could just be interpreted as a older zircon if it's in a younger rock, just because it is so durable that the older zircon from the older rock will get inherited into the younger rock. There are other complications as well, such as contamination from elements such as calcium, potassium, and iron, and these also distort the results. So they alter the isotopic ratio between uranium and lead. Also, hydrothermal alteration can change the chemistry as well because this decreases the silica content and increases trace element content. So because of this, zircon is not always a perfect closed system. In terms of petrochronology, we can deal with complications using a combination of uranium lead dating, trace element chemistry, and textural analysis. So it can help us link ages to partial melting, metamorphic reactions, and magma evolution instead of just one numerical age. This is really important for the interpretation. So in terms of zircon interpretation, zircons record a wide range of geological processes, including magmatism, metamorphism, and fluid interaction, as mentioned before. But this means essentially that interpreting zircon ages requires the understanding of the context in which it formed instead of just the age. So zircon can be described as a time capsule that preserves multiple stages of geological history within one single crystal instead of just one age. The texture is really important when looking at zircon dating as well. So one of the most important processes within a zircon is recrystallization. So this is when the zoned zircon transforms into unzoned zircon, and trace elements like uranium, thorium, and lead are lost. The crystal structure does become more stable, and recrystallization occurs because zircon that has high concentrations of uranium and thorium become unstable due to radiation damage, which makes it susceptible to alteration. So during recrystallization, the crystal will reorganize itself into a more stable structure and expel these trace elements. And this can happen during metamorphism, cooling, or fluid interaction. And looking at zoned versus unzoned zircon, so zoned zircon will have a high uranium thorium content, and it forms during the original crystallization when the magma crystallizes, and unzoned zircon has a low uranium thorium content, and it forms during recrystallization of the zircon that was previously crystallized. The difference here is important for interpreting ages, and the chemical difference is significant because it allows us to distinguish between primary magmatic zircons and secondary metamorphic zircons. So why does this matter? This matters because zircon ages do not always represent the original formation of the rock. For example, if you look at a zircon that could record 2.7 billion years for its crystallization age and 2.6 billion years for its metamorphic age, if you interpret that without using textures, you could assume it was crystallized 2.6 billion years ago instead of correctly interpreting that that was the metamorphic age. So in other words, ages must always be interpreted in context using trace element chemistry, textures, oscillatory zoning, things like that, instead of just interpreting it immediately after calculating the isotopic ratio. The key idea here is that zircon does not always the zircon age does not always equal the formation age. It could reflect recrystallization, metamorphism, or other geological events. And to conclude, zircon growth records zoning and crystal shape. Uranium lead dating gives us the age, and interpretation requires petrological textures and chemistry. So overall, zircon is not just a geochronometer, it records several geological processes over time over all of Earth's history. Thank you very much for listening to my presentation.